This animation shows biological sequence strands quickly snapping together, but then fraying and unraveling at the edges to reveal a structural failure. Clustal omega is incredibly efficient at finding evolutionary relationships among nucleotides and proteins, but feeding it raw data and trusting the default settings often results in exactly this kind of collapse. Our objective is to take raw, disorganized sequences and process them into a verified, publication-ready alignment. We achieve this by actively configuring the software's parameters rather than letting the algorithm guess our intentions. Before we begin, you need 4 components ready to go: the Clustal Omega command line tool, your raw sequencing datasets, a basic text editor, and an alignment viewer program. Treating bioinformatics software like a black box, where data goes in and answers come out, is a fast track to costly misinterpretations. Taking active control over the alignment process ensures your downstream research is reliable. Here in this split-screen comparison, you can see chaotic, unorganized text on the left, contrasting with uniform, clean data blocks on the right. Your first step is to discard low-quality sequences containing sequencing artifacts or misannotations, leaving only reliable data in your workspace. This diagram illustrates an algorithmic failure. Notice how a tiny sequence block struggles against long sequences, getting lost in large spatial gaps. To fix this, extract short sequences from your main stack for preprocessing or specialized tools. Once your sequences are uniform in length and quality, they must be saved strictly in the FOSTA format. This is the structural standard Clustal Omega expects to read. This comparison shows exactly what happens when that format is broken. The file on the right is a perfect FASTA document, starting with the required > symbol to denote the sequence label. If you skip this, as seen on the left, the software will immediately throw an error. The second FASTA rule requires that the text directly following that > symbol is completely accurate. Ensure the label is free of complex hidden characters or spaces that might confuse the command line. Finally, the sequence data itself, the actual string of nucleotides or amino acids, must be placed immediately beneath the label as a continuous block of text. Formatting your data meticulously at this stage removes the most common variables that cause sequence alignments to fail. When your inputs are pristine, you avoid hours of troubleshooting syntax errors in your terminal. With the data cleanly formatted, open your command line interface. The structure requires calling the program, defining your input file, and naming the final output file. At this point, you could simply execute the command. However, default settings are designed as a generic baseline. They rarely account for the precise evolutionary dynamics of specialized datasets. Watch how adjusting a numeric gap penalty variable physically tightens and loosens the alignment to penalize biological insertions and deletions. We also configure substitution matrices, a grid cross-referencing sequence variables, to score your alignment based on evolutionary likelihood. Next, check your iteration settings. By forcing the algorithm to loop back and refine its initial alignment multiple times, you drastically increase the accuracy of the final output. Once your custom parameters are locked in, execute the final command. The terminal will run the algorithm, and you can monitor its progress until it confirms the output file has been successfully written. Keep in mind, if you are aligning exceptionally large datasets, a local machine might freeze. Plan ahead and route heavy computational loads through high-performance computing clusters or cloud-based platforms. Customizing these parameters requires reading your data's specific needs. That active configuration separates a passable alignment from one that yields true biological insights. When Clustal Omega completes its run, the next step is opening your newly generated output file in an alignment viewer tool, such as JalView or AliView. Do not accept an algorithmic output without verification. You need to manually scan the sequence visualization and look for structural anomalies that indicate your parameters need further adjustment. This mock interface highlights exactly what you are scanning for: jagged, unaligned sequence edges and isolated floating gaps in the data columns. Finding these errors means the alignment needs correction. As you verify your files, you will also notice Clustal Omega generated a secondary output document, a phylogenetic tree file. This animation shows a branching structure strictly acting as a guide tree to order sequences for alignment. It is a rough mathematical tool, not an evolutionary phylogenetic tree. Publishing this as a definitive evolutionary history leads to false scientific claims. Rigorous visual inspection of the sequence grid, combined with the correct interpretation of the software's outputs, protects you from carrying flawed conclusions into your final publication. This glowing block of sequence data is what absolute data harmony looks like. This is your ultimate result, a biologically meaningful, error-free alignment. You reach this point by filtering out bad raw data, explicitly defining your gap penalties and iteration parameters, and manually verifying the structural output. With a verified alignment, you are ready for complex downstream applications. You can export this data into specialized software for structural prediction, or feed it into dedicated phylogenetic tools to build a true evolutionary tree. By taking the time to master Clustal Omega's mechanics, you ensure every subsequent phase of your research is built on a foundation of absolute accuracy.